Okay, now we can begin our study of physics properly, and we're going to look at a branch of physics that's known as kinematics. And kinematics is the study of motion. And I like to think of it as a description of how things move. We're trying to understand how to describe the motions of things in our universe. Now, in order to describe the motion of an object, we need to be able to locate that object in space. We need to have some idea of where it is, where it starts from. And so we developed the idea of a common frame of reference. And in order to do that, we're going to use a standard Cartesian coordinate system. Now, our coordinate system can be in one dimension, in that case it would just be a line, or it can be in two dimensions, which would be a normal XY kind of a graph. You guys know you've got the x-axis and the y-axis. Or we can do it in 3D, and we'll see how to do that in a minute. But one thing that we have to recognize is that the choice of the origin of our coordinate system, that is where we put the zero of our coordinate system, is completely up to us. We can put it anywhere we want. And that's going to be very important because it will enable us to simplify things in many cases and make our jobs a lot easier when we're actually trying to solve problems. So here we have the example of the different types of coordinate systems we might use. We have a 1D coordinate system, which is just basically the number line that you learned about back in grade school. So here's the origin, and I've got positive values, and I've got negative values. Then we can look at a more standard two-dimensional coordinate system, the standard Cartesian XY coordinate system. So I've got the x-axis and the y-axis, and each of those have positive values and negative values. And of course, the Cartesian coordinate system is broken into four quadrants. We have quadrant 1, quadrant 2, quadrant 3, quadrant 4, and then back to quadrant 1. And we've seen how to locate points in space using these. I'm not going to go over that, but I just want to point out that this is something that you should already know about. Now, here's one that you may not have seen before. This is how you do it in 3 dimensions. And so you can see that we've got the x coordinate coming out of the page here, and then the y coordinate going left to right, and then the z coordinate going up. Now, this x coordinate that's coming out of the page, or out of the screen in this case, it is meant to be coming perpendicularly out, but that's kind of hard to draw on a two-dimensional surface. So we draw it with perspective at this kind of downward 45-degree angle. But remember that this line, we're imagining it coming perpendicularly out of the screen. Now we talked about needing to define a coordinate system, and we have a coordinate system here, a three-dimensional XYZ with an origin where those axes all meet. Now the first actual physics definition that we're going to build is the concept of a position vector, or simply the position of some point in space, or the position of some object that is located at some point in space. And so if I have a vector and it's from the origin to whatever point in space I want, that is my position vector. Now, if we think about our vector being in 3 dimensions, we can note that it's going to have 3 different components. And so here along the x-axis, you're going to go out some distance, and that's called r sub x. That's the x component of the vector r. Then we're going to go over along the y-axis, some r sub y value, and then we'll go up the z-axis to the tip of our vector. And so the components of this vector are rx for the x component, ry for the y component, and rz for the z component. And of course, we know how to write that out in component form. R vector is rx in the x hat direction, plus ry in the y hat direction, plus rz in the z hat direction. So we could, of course, simply put numbers here to represent. So this r vector, for example, it might equal to 3 in the x hat direction, plus 4 in the y hat direction, plus 5 in the z hat direction. And we could say that this position vector is going to be in something like meters or feet, whatever. But in this case, we would see that Rx, that's the value of the x component, that's just going to be 3. Ry is going to be 4, Rz is going to be 5. And so that would be this particular point right here. I could, of course, draw a vector to another point. I could have a vector, for example, going from the origin to that. And then I would have different values for the components, every point in space, no matter where I pick a point in space, there will be a position vector locating that point in space with x, y, and z coordinates. Now the next definition that I want to give you is the definition for displacement vector. And the displacement vector is the vector quantity which represents the change in position. So here I've got my three-dimensional Cartesian coordinate system here again. And I've got some initial position vector which I'm calling r sub I. So I go from the origin to some point in space, and that's where I start. That's my initial position. And then I go along some kind of path. And it doesn't really matter how I got there. So I could start at my initial position and go however I want, but I end up at some final position. And so this second vector here, this is the vector, the position vector to my final position, and we can just call that r sub f. Now, the displacement is the straight vector from where you start to where you end up. So if I start at Ri and I end up there, that is my displacement vector. But let's look at this picture, because I've got my two blue vector here, my initial position and my final position. They're connected tail to tail, and then my displacement vector, that is going from tip to tip. And so this triangle represents what we've seen before as a vector subtraction. And remember, it goes from the second vector, so Ri would be the second vector, to the first vector, which would be Rf. So if we write this as a vector subtraction, we can say that the displacement vector, delta r, and when you see this symbol delta here, that's a mathematical symbol very often. It's a Greek letter delta, but it's used in math to represent the phrase change in. So if I see delta r, that means the change in r, or specifically, the change in the vector r is equal to the difference of the final vector minus the initial vector. And remember, you go from the second to the first, from the second to the first, and that's your vector subtraction. So this delta r here is going to be my displacement vector. Now, if I want to write out these all in terms of all their possible components, I can say that my initial position is going to be some x initial, it'll have some y initial, that's the y component of the initial position vector. This would be the z component, zi, that's the initial z component of the initial position vector. And so I can do the same thing for the final vector. It will have its own x, y, and z values. And then if I do my vector subtraction, I just subtract them like this. And remember, I'm going to group my x hat terms, I'm going to group my y hat terms, and I'm going to group my z hat terms. So this first term, for example, would be x final minus x initial x hat. And then I'd have a similar term for y hat and z hat. But I can just group all these together like that. And so when I group all the terms together that are like, so I group all the x hat terms, all the y hat terms, and all the z hat terms together, I end up with just this basic equation. I get x final minus x initial, y final minus y initial, z final minus z initial. But what is x final minus x initial? That's simply the change in the value of x, the x component. We can call that delta x. So delta r, the change in the position vector r, is given by delta x, which is the change in the x component, the change in y, the change in z. And of course we have the x hat, y hat, and z hats, unit vectors showing us the different directions. Now another concept, so we've got yet another definition in this presentation. This is going to be the definition of distance. And distance is defined as the length of the path on which the object traveled, or simply the length of the path. So you could imagine this could be this curved path here. It could be like some road that you're traveling with a car. And so you have this long meandering path here that you're driving to get from some point A to point B. And you could measure how long that path is. If you were driving in a car, the odometer in your car would tell you how many miles you drove. On the other hand, the green vector here is the displacement vector from A to B. And so we can see that the displacement vector is going to represent the straight line path. And of course, I could have drawn, some x, y, z here, and there would be a position vector there, there'd be a position vector up there. that would give me the position vector starting to A and ending with B, and the displacement would be the vector difference between those two. But if we're looking at just the path itself, the two ideas are we have the distance, which is the length of the path, and that's going to be a scalar. It's not going to change whether we go forward or backwards. But the displacement vector, it's from where you start to where you end up. So if I actually started at B and ended up at A, the length would be the same, the length of the path would be the same, but the position vector would point in the opposite direction. And so just be aware that when you're talking about displacement, that's our green vector up here, the displacement vector, the direction matters, like with all vectors. But with length, which is a scalar, the direction does not matter. Now, another thing that we can point out is that you don't have to go along this curved meandering path. You could imagine that there was a straight stretch of road and you're just going along a straight stretch of road. And so the distance would be along the length of this green vector here. And what would be the length of this green vector? That would be the magnitude of the displacement. And so we can see that the displacement is going to have its own distance associated with it, but that is not the definition of distance. The definition of distance is not the magnitude of the displacement vector. That's an example of a distance. The definition of distance is the length of the path. And so if I ask you on a test, what's the definition of distance? Don't tell me it's the magnitude of the displacement vector, tell me it's the length of the path. But be aware that every length is a distance, and so we can say that the length from here to here would be a distance, and that happens to be equal to the magnitude of the displacement vector. So if you calculate a displacement vector and you want to know what the distance is along that path, you just get its magnitude, because that length would be that distance. So here we can sum up what we've said. Again, distance is defined as the length of the path on which the object traveled. The distance is what would be read by an odometer or a pedometer. Some of you may have a Fitbit, the little thing you wear on your wrist, and it tells you how many steps you take in a day, or it tells you how far you walked. It's the same idea. The distance is simply the length of whatever path you walk along or drive along. And then contrasting with the idea of distance, which is a scalar, we have the idea of displacement, which is a vector. And it's the straight line pointing from the initial position to the final position. And that's really what we want to remember in terms of how to draw the displacement vector.